slightly less interesting material of the course, Evolutionary Robotics. We will finish up today. Our discussion of the minimal cognition sub-branch of evolutionary robotics, as we mentioned several times now. The idea is to look at, sort of pare down the complexity of our agents, our environments, and to some degree their neural networks, and see what kinds of building blocks of intelligence we can evolve into them. We will finish lecture 9 today. Lecture 10 is relatively short, so we may be able to start in on the second sort of sub-branch of evolutionary robotics, which is legged locomotion. What are the roots of intelligence in mobility? The problem of getting from point A to point B. Yeah. Okay. Before we talk about any of that, of course, assignments. So undergraduates, you're working on assignment 6, where you're starting to implement the neural network controller for your robot. Neural network controller is made up of a bunch of neurons and synapses that somehow wire up the sensors to the neurons. And not this week, but next week in assignment 7, when you add the synapses, you will close this loop. Your robot will now be controlled by closed loop control. It will receive some sensation from the outside world, in your case, a virtual world. Those sensor signals will flow through the neurons and synapses to the motors. The values arriving at the motor neurons are sent to the motors. The motors interpret that eventually as torques, rotational forces, that the motors apply at the joint to try and rotate that pair of connected objects. That causes the robot to move, which causes the robot's relationship to its environment to change, which changes its sensor values, and around we go. Sense, think, act, right? So far, so good? Okay. Graduate students, congratulations. You have now finished all 10 assignments. So you're not at the end, you're at the end of the beginning. Now the hard part starts, which is the final project. So I put together a document for the grad students, and it's 3 pages long, so I'm not going to read the whole thing this morning, but I do want to get the graduate students oriented on this. Graduate students, you're coming up with a final project idea of your own. We have about 10.5 weeks left in the semester. So the biggest challenge for you to solve between now and next Monday at 11:59 p.m. is, what is it that you want to do for your final project? And is it something that's reasonable and doable within 10.5 weeks? Difficult thing to do because neither I nor the TA can tell you. We have some intuition, but it's really up to you to try and decide. So at the beginning of this document, there's a pointer to the last module in the Ludobots subreddit, which is about final projects. There's a whole bunch of different final project ideas that are listed there. At this point, you can also get on YouTube and put in CS206. There's been hundreds of final projects now that have been posted to YouTube. You can sort of see things that students have done in the past. I would encourage you to try and come and see myself or the TA at some point this week during our office hours, or at least shoot us an email about what you have in mind, and we can give you some sort of feedback about whether it's doable in about 10.5 weeks. Yeah? Okay, so what exactly is it that the grad students are submitting next Monday at 11:59 p.m.? You're submitting a project description and a project plan. The description is a very short paragraph describing what you have in mind. So here's an example of a good project description. Nature has evolved organisms that walk over land with various number of legs, which we'll talk about in lecture 11 shortly. So I, the graduate student, plan to generate robots with varying numbers of legs, and then test which of these robots the evolutionary algorithm is able to evolve the fastest gaits for. There's pros and cons to having larger or fewer legs. What's the right number of legs for your robot in its virtual environment? That would be a reasonable final project to tackle. Okay. So basically, you're typing in that paragraph, copy and pasting it into your Blackboard submission, and off you go. The second part of what the graduate students are submitting is a project plan, which is, we have 10 Mondays left in the semester. So next Monday, you're submitting the project description and plan. And over the following 9 Mondays at 11:59 p.m., the graduate students are submitting 9 milestones. These are basically weekly reports which are images and videos demonstrating that you're making progress towards your final project. So grad students, you're not only coming up with an idea this week for what you want to do, but you're also breaking that idea down into 9 steps. And then along with the description, you're submitting to us 1 sentence for each of these 9 steps. So if this is my final project description, here are 9 appropriate milestones written out and submitted to Blackboard. I'm going to modify my code to turn the quadruped, which you have at the end of the 10th assignment, the 4-legged robot, into a hexapod. I'll submit a short video showing the hexapod being simulated, but it's not going to have any neural controller at this point. I'll comment out all my code that creates the sensors and motors and neurons and synapses. So basically, you're shutting off or inactivating a lot of the code you developed in the 10 assignments and then sort of turning modified stuff back on again. Yeah. I'll submit a video showing this robot being simulated, and I'll drag it around with the mouse to show that the joints are all in the right places, the joint normals are all correct. So I'm basically going to demonstrate that I've changed the body of the quadruped into the hexapod. That's what I'm telling you this coming Monday that I'm going to do for my first milestone. I propose as my second milestone that the week after that, I'll modify my code to generate 6 sensors for the 6 legs. I'll submit images showing how the values of these sensors change as I drag my robot and crash it into the ground, like we did in the sensors module. So I'll be submitting something to you to demonstrate that I've now instrumented my hexapod with sensors. The week after that, I'll do the same thing, proving that I've implemented motors. The week after that, I'll prove to you that I've added back in the neural network. The week after that, I'll prove that I've turned back on my evolutionary algorithm. So I'm now evolving gaits for the 6-legged robot. The week after that, I'll change my code so that I'll demonstrate that with changing a single variable from 4 to 6, for example, it'll generate not a 4-legged robot, but a 6-legged robot. At the moment, you're kind of hard coding the body and brain of your robot into your code. There's an idea that actually comes from computer graphics called procedurally generated content. Procedurally generated content, where you can parameterize your code, and by changing one or a few variables, it'll generate procedurally different stuff. Yeah. So I'm going to prove in week 6 here in my 6th deliverable that I've now created, I've modified my code so that it procedurally generates a 4-legged robot, 6-legged robot, 8-legged robot. The week after that, I'll show that it also now generates the appropriate number of sensors and motors and neurons and synapses for however many legs the robot should have. The week after that, I'll show that I've also made my evolutionary algorithm procedurally generated, meaning the evolutionary algorithm will look to see how many legs, how many sensors, how many motors, how many neurons and synapses, and create an appropriate genotype. The evolutionary algorithm will be able to evolve sets of synaptic weights for however many synaptic weights that legged robot needs. The week after that, the final week, I'll submit videos showing that I'm now able to evolve gaits for 4-legged robot, 6-legged robot, 8-legged robot, 10-legged robot, and I'll finish by conducting an A/B test. This is something that the undergraduates are going to be doing as well. An A/B test is an idea from engineering and also user interface design. I'm going to create 2 versions of things, or multiple versions of things, A, B, C, D. And I'm going to demonstrate to you, I'm going to provide some data showing that A is better than B, or B is better than A, or there's no difference between A and B. So I'm going to provide at the end here some data showing that when I evolve gaits for these different kinds of robots, for one or more of these robots, it's easier for the evolutionary algorithm to evolve fast locomotion for it than for the other robots. Yeah? That's just one example. So I've taken this project about exploring legged locomotion, cut it up into 9 parts, where each part builds on top of one another. And the text that I just read off to you, that's what the grad students are going to be typing up, revising, and then submitting to Blackboard. Yeah? Grad students, you don't need to really do any coding this week. All good? Any questions about that? Okay. Undergrads, thanks for bearing with us. You're still working your way through the assignments. You're going to have, when you get to the end, you're going to have 3 or 4 Mondays. You're going to do an abbreviated version of this. You can pick one of the final projects from the subreddit, or you can come up with one of your own, and you'll be breaking it down into 3 or 4 steps, however many weeks we'll have at that point, and doing an abbreviated version of this. Questions? All good? Okay, grad students, again, come and see me or Krishna in person or remotely and just bounce your ideas off us so we make sure you've got something that's reasonable. Okay. All right, back to minimal cognition. So we've been looking at a series of cognitive building blocks. What were they? We got to the last one. We didn't quite finish. You'll have to use one of these building blocks to remember what these building blocks were. We looked at 4 of them. We have been looking at 4 of them in lecture 9 here.
Remember one was affordances?
Detecting affordances was the first one, right? I look around my world and the chair or the table is advertising to me. It's shouting to me affordances. You can use me for writing, possibly for sitting. They project ways in which I can interact with them. We saw detecting affordances. What were the other 3? Selective attention, that was the last one. We'll finish that one in a moment. Selecting what you need to attend to in the world around you. What were the other 2?
Compositionality.
Sorry?
Was it compositionality?
Compositionality was, it was actually a 5th one. We actually looked at that when we looked at an example of the CTRNN. When we looked at the little robot that shook the block left and right, we looked at how it composed together motor primitives. Definitely a cognitive building block, so we'll include it. Yep. Self, non-self discrimination, arguably the first task that you needed to solve as an infant. What's the one that we're missing? What's the one we're forgetting? Ironically. Short-term memory, exactly. Okay, so we got to the 4th and final one in this lecture, which is selective attention. Arguably, for us, very difficult, and for our little minimal robots here, also quite difficult. We have our little robot moving about at the bottom of the screen. It's got 2 motors. It's little rockets that are pushing it left and right along the bottom of the screen. We've got these 2 falling objects. As you can see from the black dashed arrows, they can fall towards the bottom of the screen at different angles. They can fall at different speeds. And they also start at different vertical heights above the ground. Yeah? This robot has, as usual, 7 proximity sensors represented by these gray beams here. This robot never goes blind. It can sense and move at the same time. This is a tricky task because as the robot, quote unquote, decides which one is going to hit the ground first and goes chasing after it, it may have to remember where the other one is and or where the other object is heading and get back there after it catches the first object to catch that second object. Yeah? Fitness function, pretty much what we've seen before. P sub I, which is the performance of the robot during the ith trial. We're going to evaluate every robot, every CTRNN multiple times inside the robot, and we're going to drop several pairs of objects one after the other. For the ith pair drop, we're going to compute, the performance is going to be D sub I1 plus D sub I2, where DI1 is the horizontal distance between the robot and the first object that hits the ground, and D sub I2, horizontal distance between the robot and the second object that hits the ground when it hits the ground. Yeah? What's the best thing that the robot can do here?
Catch both of them, which would be DI1 and DI2 equal to 0.
Exactly. Both of those terms should be 0. So basically, the closer to 0 you do, the better. So when we take the summation over average, what's the average performance of the robot. They take the maximum score here and subtract off. So that basically you can just pay attention to the negative sign on the left here, right? We're always trying to maximize P. Yeah. Okay. Okay, I ended last time by showing you a final project from years past. A student actually implemented this in the physics engine we used to use and was able to evolve a robot capable of selective attention. As you might have noticed from the video, and in the interest of time I won't play it again, some of these pair drops are more difficult than others because there are two types of problems that can arise depending on where these objects are and how they fall. The first problem is the passing objects problem. The object that is initially further above the robot, further away from the robot, it happens to be moving faster. So at some point, the pair of objects are going to pass one another, and that object that was further away is actually going to hit the ground first. Yeah? Second problem is the object permanence problem. As the robot goes chasing after one object, that object might pass out of the cone of perception of the robot. It may temporarily not be able to see where that other object is and have to remember where it is and go chasing after it. Okay. It's possible, depending on how these objects fall, that the robot might be confronted with neither of these two problems, one of these two problems, or possibly both problems simultaneously. Yeah? Can you think of examples from your own life of an example of the passing objects problem? Obviously, you're not always literally catching pairs of objects, but as undergraduates and graduate students, you got a lot of deadlines, things that are approaching you in the future. What would be an equivalent of the passing objects problem?
2 large assignments due on the same night.
2 large assignments due on the same night. Okay, that would be the 2 objects hitting the ground at the same time. Very difficult. Close. Something is initially further away, but over time, something happens where you have to shift your attention to that because now it's going to arrive sooner than something else. So grad students, you've got to write your project description by next week. I'm sure you've got other deadlines. Oh, by the way, I'm now going to change the deadline and move it up till Thursday, right? Shifting deadlines, things that are further away suddenly needed to be attended to quickly. Family member calls, there's a family emergency, you got to switch attention to that. All sorts of things that are sort of in the background and then suddenly jump out into the foreground and you got to figure out how to switch. What about the object permanence problem? Think of any examples from your own life of this issue? You go chasing after one issue and a second issue passes out of your cone of perception.
If you're like focused on one assignment and you don't check your email.
Exactly, right? We live in a world where we're now controlled by machines, right? Notifications, email, Slack, Teams, notifications coming at you. Hopefully you're able to tune those out and focus for a little bit on things that are important to you. As you do, of course, you're ignoring notifications. You have to take the risk that it's okay to ignore other things for a little while, right? In the minimal cognition experiments, obviously they're almost cartoonish. They're very, very simple, but they have somewhere in there the root of real problems, real challenges that organisms and intelligent organisms need to deal with all day, every day, right? It seems like a reasonable place to start in the study of and the creation of intelligent machines. Okay, so the investigators of these experiments used these 2 problems to look to, again, analyze how does a successful robot, a successfully evolved robot do. So they evolved robots against this, evolved CTRNNs against this fitness function. When the evolutionary algorithm ended, they took out of the evolved population the CTRNN that had the highest fitness, that had the highest P, dropped it back into the robot, and dropped various pairs of objects above that robot and saw and watched what it did. Let's start up here in the upper left. Here's a easy environment. In this environment, they're going to drop pairs of objects, but the robot is not going to have to deal with the passing objects problem, and it's not going to have to deal with the object permanence problem. Let's see how the robot did in this relatively easy environment. Again, the investigators here came up with sort of this ingenious visualization, this way to watch, without watching a video, what the robot does, what's happening in the environment, all at the same time. We can see, like they've done before, on the vertical axis here, we have time unfolding on the vertical axis from the start of the experiment at the top of this panel, unrolling towards the bottom of the experiment, the end of the simulation at the bottom of the vertical axis here. What does the diagonal black line represent, do you think? The mark of a good visualization is that it doesn't need a caption, that it's often intuitive and you can figure it out just from looking at the figure itself.
It's the distance between the robot and each object?
The distance between the robot and each object, not quite, close. It's the robot's horizontal position. So you're right, in a lot of the past figures they were showing relative position. Here they're showing absolute position. It's the actual horizontal position of the robot at the bottom of the screen. This diagonal line is obviously unfolding over the vertical axis. That's time, right? So the robot doesn't move up and down. It's locked to the bottom of the screen. It's moving back and forth. And then they use the vertical dimension for time. Yeah? So we see what the horizontal position of the robot is at every point in time in the simulation. Everybody see that okay? Okay. What are the two straight black lines? What do they represent? The objects falling. Yeah, exactly. And it's the horizontal position of the objects. Now the objects do change their vertical position. They're falling. That's not shown here directly. Again, the vertical unfolding of the line is the horizontal position of that object at that point in time. So far, so good? Okay, we'll come back to the parallelograms in a moment, but you should already be able to see by looking at these three black trajectories how well the robot is doing. How well is the robot doing? You can see it zigging, zagging. And at this point, it's right underneath the object which is going to hit first. We know this object hits first because its trajectory stops early in time, right? That object is done. Then we see this straight black line continuing in time, which tells us that this black line corresponds to the object that's going to hit next. Yeah? So the robot does not just a good job, but a great job. It's immediately underneath the one that's going to hit first. Seems like it knows that that's the one that's going to hit first. The robot happens to be there when the first object hits, and then immediately heads to the second object and zigzags back and forth directly underneath it. So this is another show-off robot, showing off. It's doing really, really well, and then is there to catch the second object. Yeah. What do you think the two parallelograms represent? This one's a little trickier. You can kind of tell that the two parallelograms, the light-colored parallelogram corresponds to the object that hits first, and the darker parallelogram to the one that's going to hit second. The weight of the object could be, in this case, in these minimal experiments, the objects don't really have a weight.
Would that be like the potential trajectories it could take?
Getting there. Good ideas. Yes, in the back there.
Is it something with the robot's view?
Yes, it has to do with the robot's sensation, right? The proximity sensors. What? What does it have to do with the robot's view?
Is it like the range of positions the robot can be in where it will still see it?
Absolutely. So the hint here is that the parallelograms, or is it trapezoid? I never remember. Whatever. These polygons, They're narrowing as time goes on. So if you think about it, if we go back and have a look at the robot's 7 proximity sensors, as time goes on and these objects are approaching the bottom of the screen, there is a narrower and narrower set of horizontal positions that the robot can be at and still see the object that is now very close to the bottom of the screen. When objects are up near the top, objects are up near the top, there's a broader range of horizontal positions that the robot can be at and still see the object. Yeah, everybody see that? Okay, so given the fact that these polygons are showing you something about the robot's sensation relative to the objects, what can you tell me about what the robot sees during this simulation? Does it always see both objects? Does it sometimes see one but not the other?
It always sees both.
It always sees both. How do you know? How is this figure telling you that it always sees both?
Both cones are overlapping in the horizontal, where the robot's always in both cones.
Absolutely. The robot is always in both cones, right? So the robot can always see both objects in this case. Yeah? This is an easy one. The object that is originally closer to the robot hits first, no passing objects problem, and no object permanence problem. The polygons are overlapping. The robot can easily always see both objects and stay close and be able to catch both. Yeah? Okay. Let's look at the next one here. Take the same evolve CTRN, reset the environment, drop the pair of objects, but in this case they're going to make the environment a little bit more difficult by introducing the passing object problem. What does the dashed horizontal line represent, do you think?
When the objects pass each other.
When the objects pass one another. So now the object that's initially further away from the robot is actually falling faster. And at this particular point in time, that further away object suddenly is closer to the robot. Yeah? You've got 2 important deadlines for homework or assignments, and your professor changes one of them. So now the one that was further away and that you've been procrastinating about is now suddenly closer to you in time, and you need to select to attend to that changed deadline. Yeah? What does the robot do in this slightly harder environment? How does the robot's behavior change?
It doesn't.
It doesn't change much. The robot, it still does a great job. It catches the first object and then catches the second object. But there's a little change in its behavior. It's subtle.
Kind of sticks in between both until it can figure out which one's getting closer faster.
It doesn't seem so confident anymore, right? If we look over here, it very quickly in time starts tracking the one that's going to hit first. Here, it's sort of wavering back and forth between the 2 objects, and only quite late does it seem to center itself under the object it's going to hit first. It looks like it can't tell, it can't decide which object to attend to, which one to go chasing after first. When does it decide? When does it know?
After they pass each other.
Maybe. Hard to tell, right? So there's always, whenever I ask this question, it's always a trick question. It looks like it doesn't know until quite late. Maybe, maybe not. Yeah, hard to tell. Thinking about thinking is misleading. Okay, regardless, still does a good job. Let's look at the converse environment, opposite situation. Same CTRN, we're going to play it a third time, going to reset the environment, drop the pair of objects. We are not going to have the passing objects problem. So whatever object is initially closer to the robot, it's going to hit the ground first. But we are going to introduce the object permanence problem. Where does that problem arise? Or when does that problem arise? Again, these figures have been designed so you can see it. in the figure. What happens here? What does the robot do? And how does its perception change as it's doing it?
It moves to the right and it stops being able to see the other object when the shapes stop overlapping.
It starts moving to the right, so it has correctly determined at some point that this is the object that's going to hit first. This object is falling down and to the right. The robot goes over to the right to catch it. And at some point, as the robot is moving further and further to the right, the second object, which is falling more slowly, is going to hit later, represented by the darker polygon, the robot moves so far to the right that the robot's leftmost proximity sensor is no longer sweeping along the underside of that second object. It can no longer see it, and it can no longer see it from this time until this short time later when it actually catches the first object. What does the robot do when it catches the first object? It immediately goes back in the other direction. So it seems to know immediately or remember where that other object is. And it's racing pretty quickly. The slope of this line is relatively shallow, meaning this robot is moving to the left at a pretty good clip. Yeah? It gets there actually ahead of time and starts showing off a little bit again, tracking underneath the second object, and catches it. No problem. Yeah? Okay. All right. This robot's a little cocky, so let's really sort of challenge it. Yeah? Here we go. Fourth time, both problems, the passing objects problem and the object permanence problem. Yeah? Okay. Here's the point in time in which the further away object is now closer than the other object. And here's the point in time in which the robot, no matter where it is, cannot see both objects. How does the robot do? Okay, again, not bad. It's wavering back and forth between the two again, like we saw when it experienced the passing objects problem before. Makes sense, right? You're considering two tasks in your mind. Which one is that? Which one should I actually put some effort into now? Because that one is actually going to end up, I'm going to have to deal with that sooner rather than the other one. You know, it's often hard to deal with this. The robot figures it out, captures the first one, quote unquote, remembers where the other one is, goes racing to the right in this case, and actually gets there just in time to grab the second object. Yeah? Okay. Our sadistic investigators here did it one more time, a fifth time, but now they made things really difficult. Same thing, both problems, but now they've added an additional twist to make this even harder. What's the additional twist? Why is this fifth environment even more difficult for the robot?
The robot loses sight of at least one of them almost right away.
It loses sight of one of them, depending on where it is, before the objects pass one another. Yeah? So what does that challenge the robot to do? Why is that more difficult for the robot? If there's the passing objects problem, but it can still see both of them, it can be a little lazy, right? It can stay between and watch and just wait. The one that's further away is falling faster, so I'll just wait a while. Oh, now this one is closer and it's falling faster. It's easy. I know which one I need to go chase after. Yeah? In this fifth environment, the robot does not have that luxury. It's got to watch. There's a very, very brief period of time in here where it can see both, and then it can no longer see both. It's got to decide. Or it's got to start going back and forth between both. Yeah? Which one is going to hit first? And it can't wait until the objects have actually passed one another. You can see that in this case, despite this difficulty, the robot, quote unquote, makes up its mind very quickly. It's watching both of them, and the one that's further away, this one, It somehow knows it's going to hit first and kind of knows where it's going to hit and immediately goes chasing after it to the left, catches it. At this time, it has not seen the other object since almost the beginning of the simulation. It's been a long time since it saw that other object, and it only saw that other object for a very brief period of time. Regardless, it seems to know what to do, starts heading in the right direction, and is there just in time to catch the second object. Not bad. Yeah? Very, very simple agent, very, very simple environment, very simple physics, very simple sensors, simple motors. But if you go back and watch this video, this robot looks intelligent. It's not only behaving, it's doing something that looks cognitive. It's something that's actually difficult for us mere human beings. Yeah? That's kind of the heart of the minimal cognition experiments. You remember when we talked about the history of AI, it's notoriously difficult to actually define the term intelligence. So Alan Turing came up with the Turing test. We'll know intelligence when we see it. What we're looking at here is the physical Turing test, right? This robot doesn't talk back to us, but it acts as if it's intelligent. And maybe that's the best we'll ever do in terms of determining whether or not a machine is intelligent. Yeah? Okay. Any questions about the minimal cognition experiments before we push on and talk about the last experiment in this series? Yeah? Okay, we've looked at 5 building blocks so far. We're going to look at a 6th building block now, active categorical perception. The robot that is going to perform ACP is definitely not minimal. So we're kind of moving away now from this minimal cognition idea into more and more complex machines, and arguably more challenging or more complicated building blocks of intelligence. What is active categorical perception? Well, let's tackle each of these terms in turn. Categorical categorization. This is something that obviously is an important part of intelligence. We need to be able to categorize or differentiate between friend and foe, danger, opportunity, you name it, right? How do we actually categorize? This remains an open question. One way we may have learned how to categorize is to actually reach out in the environment when we were young and physically manipulate objects. When you physically manipulate objects, there's something magic that happens, which is based on your interaction, your physical interaction with objects, categories start to arise. Here's a simple example. Imagine we had these 11 objects. You'll notice that among these 11 objects, there are no categories. There is simply a gradual transition from one object to the next to increased or decreased roundness. Yeah? No categories here. Imagine that I blindfolded you and I put any of these 11 objects at random in front of you. You're blindfolded so you can't see them. I ask you to reach out your hand, put your hand on top of them, and then move your hand back and forth along the top of the object. Imagine you repeated this process over and over again. I took one of these 11 objects at random, put it in front of you, you reached out, put your hand on top, and moved your hand left and right. What would happen? You're now interacting with these 11 objects. The 11 objects themselves don't have a category. There's no boundary between the round and edged objects here. What happens if you started interacting with these objects in the way I described? Yep.
It'd be up to you to decide where you want to draw that line.
It could be. So you could start thinking about these objects and change how you interact with them. You might be able to influence where this categorical boundary starts to appear. Let's imagine I didn't give you that option. I didn't tell you anything about this experiment. I just blindfolded you, put these objects in front of you, and asked you to put your hand on top and wave your hand left and right on top of the object. What's going to start happening? I'm really constraining your interaction with these objects.
They're either going to roll or they won't.
They're going to roll or they won't, right? If it was on this table, which is relatively smooth, that boundary may be at a certain point. If we did this on the floor with the rug, which has a much higher friction coefficient, that boundary would be somewhere else. But that boundary would arise. For some of these objects, when you moved your hand left and right along the top of the object would roll with your hand. In other cases, there'd be a sudden difference in which the object would not roll and it would slide with your hand. Yeah? So through your active manipulation of these objects, categories would start to arise and you'd feel it. You'd feel the object, you'd perceive the object rolling underneath your hand, or you'd feel it sliding. Yeah? I mentioned last time, little kids will grab anything nearby, manipulate it, squeeze it, smash it, break it. It's hypothesized in developmental psychology, the study of how we develop from infants into adults, that this is the starting point for distal categorization, right? I see student, student, chair, chair, student, chair. I can categorize without physically manipulating things in my environment. I can do this categorization from a distance. A difficult thing to do. Maybe this was the starting point. Yeah? This is obviously not how we train deep networks to differentiate between cats and dogs in YouTube videos. They do not touch cats and dogs. They have no hands. They have no ability to actively manipulate their environment. At the moment, we force our machines to learn about categories at a distance. Several people in AI and robotics argue that's wrong. That is not the right place to start. Yeah? At the moment, it's just a matter of opinion. Who knows? Yeah? We're going to look at a robot now, which is going to be evolved to perform ACP, to categorize or distinguish between objects in its environment by physically manipulating them. As you can see already, this is not a minimal robot. It's basically an arm and hand. We are going to evaluate, we're going to evolve populations of CTRNNs, exactly like we just saw in the previous lecture, but we're going to embed each CTRNN in this much more complicated robot. And this robot is going to have to evolve the ability to categorize between these two sets of objects. Hopefully you can see visually, they're actually quite close to one another. And if you imagine being blindfolded and grasping these objects, which is the only thing this robot is allowed to do, these two sets of objects are going to feel similar to one another. This is not trivial. Yeah? The robot is going to have to evolve the ability through grabbing these objects to distinguish between spheres and ellipsoids. So far, so good? Okay. All right, let's talk about this robot for a moment. Hopefully you can see this in the back here. Actually, maybe let me zoom in here for a moment. Okay. In the arm, we have 7 joints, J1, J2, J3, J4, J5, J6, and J7. So J1 and J2, these are hinge joints, 2 hinge joints that allow the arm to move like this or move like this. When both hinges are moving, that means the shoulder can do this. This third joint, which is sort of in the upper arm here, it allows the twist, yeah, that we have in our shoulder. Your shoulder allows 3 degrees of rotation. J1, 2, and 3 allow the same thing for the shoulder and upper arm of the robot. J4 is the elbow. J5 allows the hand to rotate all around the long axis of the lower arm, like your hand and your lower arm. 6 and 7, this is 6, and this is 7. Yeah? Very, very much like our anatomy. The title for the paper that we're drawing this experiment from today, they talk about an anthropomorphic robotic arm. Anthro meaning human, pomorphic meaning in the shape of. So clearly not minimal. They built in a lot of human anatomy to this robot. Okay, that's the shoulder and arm. Let's look at the hand. The hand's got a lot of things going on in there. You'll notice all the light blue cylinders. Those are all hinge joints. Pretty much all of the ones that you have. You'll notice numbers 1 through 10. These are the 10 touch sensors, and they're all on the palm side of the hand. There are no touch sensors on the back of the hand, which is actually an anthropomorphic detail. You have much more tactile sensation in the palm of your hand than you do on the back of your hand. You can play a game with your friend where, again, you close your eyes and you ask your friend to touch various points on your palm or on the back of your hand, and you have to report where they touched. You'll see that you will do a much better job with the palm than the back of your hand. Why? Why do we have more tactile information in our palms than in the back of our hands? It's the way our hands are shaped, right? Most of us don't grab things like this, right? There's no need for a lot of tactile feedback in the back of your hand. Yeah? Seems like kind of a detail, but again, these investigators were interested in making something that was pretty close to human anatomy, at least for the shoulder, arm, hand complex. Okay, so that's the robot's anatomy. As I mentioned, we're going to evolve the robot to categorize between these two pairs of objects, these two types of objects. They're going to evaluate every CTRNN 16 times on the robot and compute the performance of that CTRNN as the average behavior of the robot over those 16 trials. Yeah. How are they going to do this? In the first 8 of the 16 trials, they're going to set the robot's initial pose to pose A or position A. They're going to set the position to pose A, put this object underneath the object's palm, see how the robot does, then reset it to position A, put this object under the robot's palm, see how it does, reset it to A, evaluate it a third time, reset it to A, evaluate it a fourth time, fifth, sixth, seventh, eighth. On the 9th of the 16 trials, they're going to set the position of the robot to position B, put this object underneath. On the 10th time, reset the robot to position B, put this object underneath, back to B, this object, back to B, this object, this object, this object, this object. I haven't said exactly how they compute fitness yet, but you can probably guess. This robot is going to have to do something to show us that it thinks it's in contact with a sphere or an ellipsoid. Why these 16 trials? Why not just evaluate the CTRNN twice, once in the presence of the sphere and once in the presence of the ellipsoid? That hypothetical experiment would go 8 times faster because every CTRNN is only being evaluated twice. Why evaluate every CTRNN 16 times?
Because the ellipsoid will feel different depending on its orientation.
Absolutely. So these 4 different orientations of the ellipsoid are going to feel different, but they're the same object. Yeah. I'm sorry, I skipped over this, so I wanted to come back to this. When an organism or a machine is attempting to perform ACP, there's an infinite number of actions you can perform with objects. What are those actions designed to do? They're designed to do 2 things, possibly at the same time. Reduce within category differences. I don't know how many of you reach out for your cell phone in the middle of the night, the lights are off, you're fumbling with the phone. You're manipulating the phone until you mentally know, okay, I know how I'm holding the phone, I know where the turn off the alarm button is, right? You're manipulating the object to reduce within category differences. I mean, it's the same cell phone every night, but when you initially grasp it in the middle of the night, you're getting sensory differences. You're manipulating so it feels the same. You're holding it in the right way every time. Yeah? Alternatively, when you're manipulating one object and then another one, you might manipulate those objects to magnify between category differences. If you were asked to reach out blindly and grasp some of these objects, how might you manipulate them to exaggerate the felt differences between a grasped sphere and a grasped ellipsoid? How would you exaggerate the categories between how would you exaggerate the felt differences between these two categories?
My instinct would be to like toss it in my hand and kind of rotate it a little bit.
Okay, yeah, you could toss it up in the air and kind of rotate it, feel how it comes back into your hand, right? You're acting and feeling the sensory repercussions. That might exaggerate the felt differences between a sphere and ellipsoid. You might kind of pinch the end, or even pinch to feel whether there is an end, right? Lots of things you can do. Yeah. You've all spent time in student housing. Your roommates are always drinking your milk. You reach for a container. You pull out the container of milk, and you can manipulate it to feel how much milk there is in the container. There's an infinite number of ways you can move the container where you can't feel so much how much milk is in the container. We do this all the time. Again, you're not really aware of it, right? We act sometimes to help us recognize the familiar, fumbling with our cell phone in the middle of the night. Sometimes we act in a way to magnify differences. This could be A or B, I'm not sure. If I grab in this way and I feel this in response, it's probably B. Yeah? Questions, comments? So far, so good? Okay. All right, so we can see why we're doing these 8 trials with ellipsoids at different orientations. They also place the sphere at different orientations, just to be fair. Of course, a sphere doesn't really have different orientations, so that doesn't matter too much. Why 16? Why not just the 8? Why test each CTRNN 8 times starting from this position? And why test the same CTRNN on these 8 objects starting from this position?
Is it maybe like doing something different between the positions? Like one position it folds around, the other kind of like grabs it?
Could be. The robot could evolve to do different actions starting from these different poses to distinguish between spheres and ellipsoids. Maybe. We haven't got to what it does yet. Why are the investigators forcing it to do this whole thing all over again twice, starting from A and then B?
It just generalizes better.
Generalizes better, right? They want the robot to be able to distinguish between spheres and ellipsoids, regardless of the orientation of the object, and regardless of the starting pose or starting position of the robot. Yeah? Okay. All right, how are we doing on time? All right, so here's the CTRNN that controls this robot. As you can see, it's also not minimal, so we're starting to add in a fair bit of complexity. I like this figure from the paper because it simultaneously shows a graphical representation of the CTRNN and a mathematical description of exactly the same CTRNN. So we can jump back and forth between these two, and this is a nice scaffold to help you build up and solidify your intuition about how to describe CTRNNs or neural networks in general mathematically. Let's start with the graphical representation. On the bottom row here, we have all 22 sensors that are inside the robot. The top row here, these are all the motor neurons or the actuator neurons. Actuator and motor, for our purposes, is going to be exactly the same thing. There's 2 special neurons out here, the 47th and 48th neuron. We'll come back and talk about those in a moment. And then there's 8 hidden or internal neurons between the sensor neurons and the motor neurons. Why 7 arm proprioceptive sensors? What are those 7 proprioceptive sensors sensing? Exactly, right? There's 7 joints in the arm. There's 1 sensor sitting on each of the 7 joints, which is sensing the angle of that joint at a given time. Yeah. Proprioception is basically sort of your felt internal experience, the orientation of your own body. I don't have to see my arms to know what they're rotated to. I can feel it using the proprioceptive sense organs in my arms. Yeah? We have 10 tactile sensors, which we already talked about. They're the 10 touch sensors in the hand, one in the palm, one in the thumb, and then 2 each in the remaining 4 fingers. And we have 5 hand proprioceptive sensors. It's not so clear from the figure here. The 5 proprioceptive sensors in the hand are sensing the angle of rotation of the 5 fingers, not the individual angle of the joints inside the finger. Inside each of your fingers, you have 3 rotational joints. For most of us, you cannot rotate each of those 3 joints independently. You can try this if you want. Very, very difficult. Not impossible. Same thing for the robot here. As you'll see in a moment, there's going to be motors that send signals to the 5 fingers as a whole that cause the fingers to either curl up, flex inward towards the palm, using our language from before, flex inward, or extend outward away from the palm. Yeah? 7 sensors in the arm, 10 touch sensors in the palm side of the hand, 5 proprioceptive sensors in the fingers. We've got all of these sensor neurons connected by synapses to the hidden neurons or the internal neurons. What does this arrow here represent?
So recurrent neural network.
Recurrent connections, which reminds us or gives us a hint that this robot can remember things from previous time steps. Yeah? Okay, we have 14 arm actuators. This is a little puzzling. We have 14 motors in the arm, but only 7 joints. This is also a detail of human anatomy. So we've got, at every time step, we have 14 values arriving at these 14 neurons, and those 14 numbers are being sent to the 7 joints to cause them to rotate. Why is it not 7?
Our muscles can really only pull and not push, so you need one for each basically direction to pull on, to pull left or pull right, because you can't push and pull with one lever.
Absolutely. Muscles only pull, they never push. So all of the musculature in your body is arranged around the agonist antagonistic pattern. So for every major joint in your body, your elbow, your knee, your shoulder, there are pairs of muscle groups that pull to flex while the other set relaxes, and then it switches. The other one pulls and the other one relaxes to extend, flex, extend, right? So they're doing the same thing here. They have 14 motor neurons. They group them into 7 pairs. And within each pair, they take the 2 numbers and they basically subtract them. And that number is the single number that gets sent to the joint. So they're kind of cheating a little bit. They tried to get pretty close to human anatomy. They didn't go the whole way. You can do that with springs and motors, and we'll see that in a few weeks in another robot. They're sort of heading in the direction of trying to get that particular detail of human anatomy right. Okay. 2 actuators for the hand. Why 2? There's all sorts of joints in the hand, just 2 numbers. What are those 2 numbers doing to the joints?
Maybe finger and thumb.
It could be fingers and thumb. Not quite. Other ideas?
Is it open and closed?
Open and close. So they're using the same agonist antagonistic idea. Yeah, either extend open or flex open, or extend open, flex inward. Yeah. Okay. Let's very briefly look at the math down here. We have a total of 48 neurons in this CTRNN. So we have 48 ordinary differential equations. We have y sub 1 prime. We have a second ordinary, an ODE that describes the rate of change of the second neuron, third neuron, fourth neuron, and so on. We got 48 ordinary differential equations. In the first 22 of those 48 differential equations, the differential equation only looks like this. We only have a tau sub I, and we only have a gain attached to I sub I. What is I sub I? Again, I hate this notation, but we're stuck with it. It's somebody said the sensor, right? So basically, the rate of change of this neuron is mostly influenced by the sensor value coming in from that sensor. Yeah. Now, that sensor neuron can have its own tau sub I, so that its rate of change might be relatively slow or fast in response to changes in that particular sensor value. Yeah? Okay. For all the other neurons, neuron 23 through 48, we have a more familiar looking ordinary differential equation. Each one has its own tau. It's relaxing back to 0, and we're summing over all of the incoming synapses to that neuron. We're missing one of the parameters from the full CTRNN. Which one is it? Anybody remember? Short-term memory. It's the gain. We have the gain actually in the sensor neurons. We have no gain in the internal and motor neurons. Why this particular detail? I have absolutely no idea. Okay. Last detail of the math here. For neurons 23 through 30, which if we jump back to the visual representation for a moment, represent the internal neurons, we're going to sum up all the influences in this summation term for those neurons from n equals 1 to 30. What does that represent here? What does that tell us? What does that tell us about the connectivity in this CTRNN?
The output neurons don't feed back into the internal neurons.
The output neurons don't feed back in, but for each of these 8 internal neurons, every neuron in there is receiving 30 incoming connections. Synapses that are coming from all of the 22 sensor neurons plus the 8 hidden neurons. So that includes recurrent connections and self-connections. The IF hidden neuron sends out a synapse that connects back to itself. Everybody see that? Okay. For the 31st through 48th neuron, which are these up here, these are receiving 8 incoming connections from the 23rd through 30th neuron inclusive. So each of the 8 hidden neurons here sends an outgoing synapse to each of the 18 motor neurons out here. So far, so good? Okay. Okay, so they're going to create a population of random CTRNNs. Each CTRNN needs to encode values for all of these parameters over these 48 differential equations. We take each CTRNN, plug it into the robot 16 times, and we want a fitness function that's going to tell us how the robot did at distinguishing between spheres and ellipsoids. You could probably already guessed that it's going to tell us at neurons 47 and 48. Remember, at every point in time, there are 2 values arriving at 47 and 48. How might we interpret those numbers? How might we take those 2 numbers and plug them into a fitness function to compute how well the robot is distinguishing between spheres and ellipsoids? Different ways we might be able to do this. Ideas?
You'd say, like, if it says, well, you can normalize the values after you get over, like, do a softmax. And then you'd say if it's 1 for 47, then it thinks it's a sphere. And if it's 1 for 48, it thinks it's an ellipsoid. And combination of the two. So you could say, well, it thinks it's probably this, but maybe not.
Absolutely. We could say 47 is the sphere neuron and 48 is the ellipsoid neuron. If the value of 47 is larger than 48, that's the robot saying, I think it's a sphere. If the value of 48 is larger than 47, that could be the robot telling us, I think it's an ellipsoid. And as you mentioned, the amount of difference between these two numbers could represent the robot's confidence about its guess. Was there a question over here?
Oh, I guess I thought it would just be like length or width or something.
Oh, it could do that too, right? There's different ways we could do this. We could interpret the two numbers as the robot's guess about the length and width of the object under its palm. Yep, another great idea. The investigators did not do this. They did something much more complicated, which we'll get part of the way through in the next 9 minutes. Before we talk about why they did something more complicated, anyone want to take a guess for why they did? Why didn't they go with one of these two simpler options?
It'd be more difficult to define a fitness function that trains in the way you want it to.
Could be that these simple choices are going to make it really hard for the evolutionary algorithm to evolve CTRNNs to do this, to distinguish between spheres and ellipsoids. Let's say we went with your idea. 47 is the sphere neuron, 48 is the ellipsoid. What if we redo this whole experiment, but now we threw cubes underneath the robot's palm as well? Distinguish between spheres, ellipsoids, and cubes. What do we need to do now?
Add a third categorization.
Add a third. Now we're going to throw prisms underneath the robot's hand, right? We could keep coming up with new kinds of geometries and throw them under, add them to the experiment. We'd have to keep tacking on more and more neurons. This is problematic. Where have we heard this problem before? Or why is this problematic?
It takes too much space.
It takes too much space, right? You've only got so much space in your skull. Your brain can't get much larger, but you keep learning throughout your entire life, whether you like it or not. Evolution has found ingenious ways to pack more and more knowledge into the same amount of neural real estate. There's different ways you can do that. In this experiment, the investigators came up with a way to allow evolution to pack more and more object categories into this neural real estate. They left it up to the evolutionary algorithm to see whether and how it could do it. Yeah? Okay, so let's see how they did that. They started by observing how not just the values of the 47th and 48th neuron, but they watched how these two neurons' values changed over time. Remember the 47th and 48th neuron, like the other 46 neurons in the robot's brain, are changing continuously. They're changing according to this ordinary differential equation. So we can draw this visually. Imagine that the value of 47 and 48 in some random CTRNN at the beginning of a simulation start with these values. Actually, maybe they better to start at 0, 0. Both of these two neurons have values 0, 0. The simulation is turned on. Values start arriving at the input layer. They propagate up to the hidden, then to the motor layer, and into 47 and 48, so that at the next time step, we'll call this t sub 0 for the first time step. At the next time step, these two neurons have new values. At time step 2, they have another set of two values, then again, and we can actually watch how these two neurons' values change over the length of a simulation. Yeah? Has anybody seen this kind of visualization before? We're watching some variables change over time, and we're drawing how they change over time in this two-dimensional figure. Anybody seen this before? I see some nods. Do you remember what this particular diagram is called? This is known as a phase diagram. If you study dynamical systems, things that change over time, this becomes your best friend. A good way to draw how things change over time. in this experiment, what we're going to see is they didn't just watch the values of these two neurons change over the entire simulation. They only watched the last 5% of time. They're only watching the last 5%. They're assuming that they're going to give the robot some time to fiddle with whatever object happens to be in front of it. And they're going to use this data, these pairs of values, to interpret what the robot thinks about the object that's in front of it. Okay, how do they do this? They're going to define a few variables. They're going to ask the agent or the robot to represent the experienced object. Is the robot experiencing or in the presence of a sphere S or an ellipsoid D? By associating with that object, they're either going to place an S or a D underneath the robot, and they're going to use these neuron values in computing the fitness function to construct a rectangle R sub S or R sub D, where the vertices of these rectangles are defined by this trajectory. They're basically placing a bounding box around this trajectory. So let's have a look at the math. They're looking over the last 5% of time. If uppercase T is the very last time step in the simulation, they're going to look at all the lowercase t's between 0.95 uppercase T, 95% of the way through the simulation, to T, the end of the simulation. They're going to look at all the values of the 47th neuron and take the minimum value among all those of the 47th neuron. And remember, we're pushing this through the activation function. The values coming from neuron 47 are going to lie between -1 and +1. They're also going to look at the minimum value of the 48th neuron during the last 5% of the simulation. Yeah? So the lowest value of this neuron, which is this value here, and the lowest value of this neuron here, the lowest value of 48 is right here. That's min from this equation. So far, so good? They take the same pair of values, and they're looking for the maximum value that the 47th neuron ever has, which is right here, and the maximum value that 48 ever has, which is right here. And using this pair of mins and these pair of maxes, that defines this rectangle in the phase diagram of these two neurons. Yeah? Seems kind of odd at the moment, but they're sort of putting a bounding box around this range of values. Okay, I think we'll pause here. We'll finish this off on Thursday. We have a quiz due tonight. Undergrads, you're working on assignment 6. Grads, you're starting to think about your final project. Have a good rest of your day.